received 2 PhD degrees, one from University of Calcutta and the other from Imperial College London. He joined the Indian Statistical Institute, known as ISI Calcutta, in 1975 as a CSIR Senior Research Fellow, where he became a full professor in 1987, a distinguished scientist in 1998, the director in 2005, and finally he was president in 2022. Currently, he is a National Science Chair at ISI and also Emeritus Professor at ISI Calcutta. He founded the Machine Intelligence Unit and the Center for Soft Computing Research Center in the same institute. He is a former distinguished professor of Indian National Science Academy and professor of Indian National Academy of Engineering, Jawaharlal Nehru Fellow, and J.C. Bose National Fellow. He worked at the University of California, Berkeley, University of Maryland, College Park, Johnson Space Research Center, US Naval Research Academy. He has held several visiting positions in various countries, for example, in Italy, Poland, Hong Kong, and Australia. He has co-authored 21 books and about 500 research publications in the areas of pattern recognition, machine learning, image or video processing, data mining, wave intelligence, soft computing, bioinformatics, social network analysis, and cognitive machines. His Google Scholar H index is 80 with about 35,000 citations. Professor Paul received several national and international awards, including Padma Shri, S.S. Bhatnagar Prize, G.D. Birla Award, NASA Technological Brief, and IEEE Fellow Class Golden Jubilee Medal. He is a fellow of the IEEE, TOAS, IAPR, International Association for Pattern Recognition, IFSA, International Fuzzy System Association, and all the National Academies of Science and Engineering in India. Today, he will be speaking on pattern recognition, machine intelligence to data science, pattern recognition, machine intelligence to data science, like Professor Munjal, towards quieter technology. This is also from pattern recognition to data science, evolution, challenges, and concerns.
Thank you very much. Thank you. Good morning to everybody. It's my great pleasure to stand in this podium of Indian National Science Academy, and I thank the committee who has selected me. The way I have prepared my talk, it's a highly interdisciplinary, and I will not use any kind of mathematics. I will just explain with examples and concepts. And this lecture would have been better for going for 1 hour, but since I have restricted, so I have deleted many slides. So if you have any question, I will reply. So it's my journey in brief over 47 plus years, because I joined my institute on 1st of March 1975, and my topic of research was pattern recognition, and I had only 2 edited volumes in Indian Statistical Institute, no journals, nothing, that time. And today data science AI is a buzzword. So every 10 years, Americans throw some buzzword. And we all Indians, China, all world, we just run after them. We get funding provided America, and then new journals also come up. So this is one of the buzzwords now going on. Our central government has started AI for all. If you go to any engineering college, IIT, I was involved, data science and AI course in BTech, data science course in MTech. Then if you go to private college, university, because I am now AICT Distinguished Chair Professor, so I am traveling. So there also says, sir, funding students, if you do mechanical, electrical, civil, no job. If you say computer science, data science, cryptology, you give 1 lakh, and for other discipline, we give 50,000. And we do not get any student for other engineering, only on computer science. So it's a buzzword, but it has good prospects, academic R&D, so evolution over my one. So only 2 edited books by K.S. Fu from Purdue. That's what I research started. So I'm grateful to my first mentor, Professor Gautam, who gave me this topic, pattern recognition. And I started as a CSIR Senior Research Fellow that time. So my talk will be pattern recognition in 75, expert system in 80, the way Americans brought those topics as buzzwords. Then data mining in 2000, big data 2010. Now we are talking deep learning. And every time I am putting in one, new technologies come up, and we have developed new technologies from my institute. Here also, soft computing came out, granular computing, example. And last slide will be more important, those who are beginners and also live, because there are certain concerns. If you do not know the parent subject, then you will be in a duck soup. Now, pattern recognition in a nutshell, it has basically 3 blocks: measurement, feature, decision. You take any object, just like I'm saying, human face, Haitian character, weather map, whatever you take. You extract certain measurements. Measurements could be numerical, measurements could be non-numerical. For example, when you go to a medical doctor, you tell your symptoms in terms of, doctor, my temperature is high, low. So it's a linguistic, non-numerical. So out of those measurements, you throw away something, because this could be redundant. So in the process, you reduce the competition time, and you increase the inter-class separability, and you enhance the inter-set separability. Then you make a decision space. But this system is pure. If there is any kind of uncertainty arising from incompleteness, vagueness, missing information, that creates uncertainty. You cannot remove uncertainty, but you can handle uncertainty, reduce uncertainty. Example, suppose you want to classify 2 communities, Bengali and Punjabi. Please do not mind if there is my Punjabi friends. So you go to Punjab, Bengal, you take height, weight, complexion, whatever you feel like. Then you see that if you take only height and weight, most of the Bengalis, they have low height, less height, low height. Punjabi is more. But you can argue, no, there are many Bengalis also. But I'm just considering ideal. So if you see that out of those, this is my feature space. Then I put a straight line, y equal to ms plus c. I call it classified design. So I go to Bengal, Punjab, you pick up 100,000 samples, label samples, I call it training samples, and based on this, I draw the line y equal to mx. I still only store m and c. Now I take an unknown either from Bengal or from Punjab, not from Odisha or Tamil Nadu. I put a scale, height and weight. It's a vector. If it falls upside, I call Punjabi, other Bengali. If it's on a line, I call it indeterminate decision. I make the decision with a toss. This is a simple classifier design. Now here the challenge is, you are given only 1,000 samples for Bengal and Punjab, and you are asked to identify all Bengalis and Punjabis. That is the challenge. That means, based on a incomplete information, you are asked to estimate the entire community. Now, on the other hand, there is another task where you are given all the samples, but no class information. For example, our NRC in Hyderabad, they are by satellite, they are taking images of the Mother Earth. But they do not know which part of Mother Earth they have come. So whether it's water, vegetation, water body, habitation, concrete, you do not know. So there the task is how to partition them into meaningful homogeneous pocket. The term meaningful is subjective, therefore you can have various solutions. Example, in a family, we have say 4 members. Typical family, father, mother, son, daughter. Now I am asking you to partition them into meaningful homogeneous pocket. If you go age-wise, father, mother, son, daughter. If you go by sex-wise, this community. Blood chrome. So you see, you get 3 possible solutions. This is what is called clustering. So in case of classification, what are the challenges? Incomplete information is given of the pattern space, and the challenge is to estimate the unknown. You have abstraction, that means you have y equal to ms plus c pertaining, followed by generalization. If you have better abstraction but more generalization, that classifier is not good. That means it is overlearning. On the other hand, in clustering, we have entire data is given, and the challenge is to partition into meaningful region. Number of regions may be no known one. It's called unsupervised supervised learning. So the learning concept was there, 60s, 70s. Now, life is not so good. If you have a simple classifier, linear, hyperspherical classifier, piecewise linear classifier is a 2-class problem, overlapping classifier, circular, hyperparabola. So depending on this, your money and requirement, you go to linear to null, highly non-linear. This is a challenging area. Here, any point can belong to more than 1 class. But statistical decision theory says either you belong to 1 class or not. So here the technology challenges was how to handle those overlapping classes. Still, this is a challenging research area. So probability theory is, everybody knows, is characterized by probability distribution function. Then fuzzy set theory came by Professor Lafayette from University of California, Berkeley. He said, no, fuzzy set theory is a non-parametric. You do not need to know the distribution. It is characterized by membership function. What is the difference? Both lie between 0 and 1. Here it is probability distribution means number of times an event has occurred. But here it is compatibility of an imprecise concept with compatibility of an object with an imprecise concept. So imprecise concept means a tall man, beautiful lady, old women. So these are all fuzzy terms. So here the merits were membership functions are flexible, membership functions are context dependent, that means same old man or same tall person in different countries, they vary. And fuzzy set is reputed for flexibility, uncertainty analysis, and getting a model linguistic input. This means low, medium, high, all kinds of linguistic information. So the challenging was, that time when we started research, bringing out the root relation between abstract concept fuzzy set, there is no relation, task or pattern evaluation. So we brought out the concept of, it's a notion of multi-class belong. That a pattern has a right to belong to more than 1 class. And similarly, in a gray-tone image, if you look at this, it's a sinusoidal variation. So if I ask you what is the boundary, if I say yes, here, it commits an error. So it is not wise to make 0, 1 boundary for a region. So a grayscale image with sinusoidal value, it is logical and appropriate to have fuzzy or ill-defined boundary, ill-defined region, ill-defined edge, ill-defined corner, relation, etc. Based on this entire image processing using fuzzy set is based on. And our first article on fuzzy set is speech recognition from Indian statistics in ITB transaction 77, and from Imperial College electronics later 1980 when I joined in 79. Now, Americans, we thought, pattern has limitation. Why? Because it takes measurements, features, they're classified. That's not the way human mind works. So, expert system came. It became a buzzword. What expert system? Say medical expert system, law interpreter expert system. You go to a medical doctor, you tell your problem, him, her. She doesn't draw mathematics on one. Based on her knowledge, she makes a decision. Law interpreter also same thing. So they use some kind of if-then rule, where you incorporate experts' knowledge. And here comes the question of probability theory between antecedent and consequent, fuzzy logic, rule-based, then rough set cropped up. It was explained by an applied mathematician from Poland. And I picked up the subject when I was working at NASA Johnson Space Center. So all these are doing uncertainty modeling, and in the process, new terminology like rule learning, rule adaptation came, and it gave birth the concept of artificial intelligence and machine learning in 1985. What is machine learning? In one sentence, learning from previous examples, learning from previous samples. And if you look at this, it is Alan Turing back in 1947 in Mind Journal, and his lecture in London Mathematical Society in 1945, he mentioned, what we need a machine that can learn from the environment. So the concept of machine learning was already envisioned back in 1945. So envision of intelligent machine. And meanwhile, we have reappearance of artificial neural network as a machine learning paradigm. I will explain those characters later on. But unfortunately, lack of adequate data, processing power, and storage, the subject did not survive. In my institute also, we introduced AI courses for 3 to 4 years. But there is no job because there is no data availability, etc. So then, knowledge-based system came after 10 years. What is the difference? It's an advanced version because you take the domain knowledge and call it knowledge base. You use reasoning to derive new knowledge out of the domain knowledge. And use semantic information, syntactic, pragmatic in the rule base as well as the interpretation to make the system more intelligent. And in the process, you have the new terms like knowledge representation, case-based reasoning, just like medical doctors or law interpreters take. Based on certain cases, they make the reasoning. Information retrieval, and India had 5 nodal centers, one in TIFR, in Institute of Science, Indian Statistical Institute, Kanpur, CDAC Pune, 5-year UNDP project. And that time is a new technology. Every time some new technologies have cropped up. Emergence of soft computing technology. What is the characteristic? It is flexibility, tractability, low-cost solution, human-like decision making. Example of soft computing. Suppose you are, if you know parallel parking, if you know driving, the first test you ask, if you appear in United States, they ask to make parallel parking. I learned driving in Houston, 3 times I failed because of this parallel parking. You have to put the car one. So why? If you know parallel parking, it takes few minutes. But if you are asked to solve this problem precisely, that is, you leave your car 6 inches from the car, that is footpath, and exactly between 2 cars, then it will take hours of maneuvering. So now the next question is do you need this kind of precision? No, we do not need. Because precision carries cost, sometimes it is meaningless. So the objective is to exploit the tolerance for imprecision, uncertainty, approximate reasoning, and partial truth in order to achieve those fair characteristics, tractability, robustness, low solution cost, and close decision making. And at this juncture, it was defined that it has 4 components: fuzzy logic for imprecision uncertainty, neural computation for machine learning, genetic algorithm for search and optimization, and it was newly introduced after 10 years from our group, handling uncertainty from granularity. Here, uncertainty arising from overlapping concept, overlapping region, overlapping classes. Here, uncertainty arising from granularity. So if you bring probabilistic uncertainty, then it will be even more powerful. In the challenging areas, in soft computing, they do not fight with each other because every technology has a limitation. So other technology takes care of this. So complementary is not, they are not competitive, but they support. And it was argued that it is soft computing rather than hard computing which should provide the backbone of modern artificial intelligence. So what was the challenging then? How to exploit the merits of individual tools and integrate them judiciously in order to obtain application-specific merit. Application-specific merit means the merit which you cannot achieve by using the individual tools alone, but you can achieve by putting them together by making synergistic integration. Example, neurophagy. It was a well visioned. You have neurophagy camcorder, neurophagy television, you have fuzzy vacuum cleaner, neurophagy refrigerator. So in case of pattern recognition, what we do? We wanted to exploit the merits of artificial neural network for generating nonlinear boundary and fuzzy set for uncertainty modeling. Before that, I explained the characteristic of artificial neural networks for any design engineer would love to have. Adaptivity, that we adjust to change in the environment, just like human being. Whenever they go to any environment, they can adapt nicely with the environment. Speed via massive parallelism, fault tolerance to missing, confusing, noisy data, ruggedness to failure of components. That means like human mind, if your brain gets hurt, you do not die suddenly. It's called gracefully digression. If any neural network, if you cut down one or two linked nodes, it will work. That is called ruggedness, optimality. And all these parameters, characteristics, any design engineer would love to have in his or her system. And another criteria, it learns from examples. If you give A, then Y. If X, then Y. Then if A, then C. You give examples, it learns whatever complication be, and is learning in made in the network parameters, input-output relation. That's why it's a very good candidate for machine learning in 80s. So we had lots of publication, lots of journals, neural net, and everybody expected neural network will solve your problem. Chemistry, physics, if you have data, you have neural net. Subject collapsed after 7 to 10 years because they lost interest. They could not solve the problem. It was too much expectation. That's what I'm apprehending now is deep learning also. So this is an example. So you buy a neural network which can accept numerical input and output 0, 1. But we have put low, medium, high. Boundary could be overlapping. And during training, using gradient descent search, we, instead of throwing the maximum output node, we pass it to different nodes. That means boundary will not abruptly jump. Boundary will slowly run. And as an advantage, it handles imprecise input, uncertainty arising from overlapping classes, can handle linguistic input in addition to NO. And it is integrating the nonlinear boundary capability generation capability of neural network with answer. And this paper received 1994 Outstanding Paper Award that time. Now look at this. This integration was starting 1992 paper, 2 years before 90. But then Lafizade came, and accordingly we defined machine intelligence is a core concept of grouping all the advanced tools with the basic concept of pattern learning. And this list is not exhaustive. As time goes on, depending on the data, depending on the technology, depending on the need of the society, these new technologies will be added up. And intelligent autonomous systems are physical embodiment of machine intelligence. So if you see that rough set, probabilistic reasoning, approximate reasoning, case-based, these are all new terms. Everybody knows probabilistic reasoning, but these two terms came up newly. Similarly, all kinds of hybridization. Now, one note as I mentioned, although Lafizade formally defined the concept of COVID-94 in different, but it's different challenges between these components were all addressed much before 90 or before that. So many people don't know. He just brought them under one umbrella in Communication ACM 1994. Then around 2000, people started talking about data mining. Data mining, just after 10 years again. What was the, at our DST, Government of India established its first center in the Asia at ISI Kolkata under its IFA scheme, Center for Soft Computing Research in 2004. Now in 2000, around 2000, because of this genome project And because of WWW, World Wide Web, your data generated become large and heterogeneous. And therefore, to handle this one, we're talking about data mining. But data mining term, if you look at the library, even in 70s, statistical patternization, I saw the word. But that time, we didn't have smart computer, smart software, and also data. So, for example, if you go to healthcare data, if you go to a medical doctor, he or she writes a prescription, many spelling, there is spelling error, incomplete sentence, uses color, uses text, uses numerical, so it's called heterogeneous data. That means numeral, text, cross, tick, tack, yes, no, color. Moreover, if you go to hospital only when you are sick, so therefore the data you get more for the disease than the normal. And our statistical patternization used to say number of samples would be much, much larger than the number of features. But now, because of the genome project, number of the genes, few thousands, number of samples, 10, 20, 50. So everything became topsy-turvy. So what you could develop and use before 80s, no longer useful. It's called small sample, large feature problem. Statistical patternization guys, they are also fighting for this. And accordingly, we had two new disciplines, bioinformatics, every IIT engineering college are bioinformatics, and web intelligence. Then in terms of patternization, whenever some subject comes, I always consider in my way how to define in terms of pattern recognition. So in patternization, machine learning principles, when applied to a very large heterogeneous, large in terms of both size and dimension, I call it data mining. And data mining has no meaning unless you have natural language processing by way of knowledge interpretation. That means you put it user-friendly. It's called knowledge discovery. And it is a process of identifying valid, novel, potentially, and ultimately understandable pattern. And in the process, granular computing came because we have a large heterogeneous data. So in order to handle the heterogeneous data and large, you need a new technology also. So there comes the granular computing. What is granular computing? Is based on information granules. Suppose, see, I'm looking at the audience. I can see some lady, pastor. I can see some old man. I can see some younger generation people. So without looking at individual audience, I can see that it's a cluster of some old people, cluster of women, cluster of young people. This is called granule. If you look at any scene, water body, sky, vegetation, habitation, we can call it granule. So I extract some clusters. I call it information granules if I represent in terms of equation or rule. So having those which are defined as a indistinguishable objects drawn in terms of property like similarity, functionality, in case of bioinformatics data, in terms of functionality, similarity. In case it's a vector space, we go in terms of similarity, physical proximity, and use those granules and forget about data for performing following tasks. And since granules represent one kind of compressed information, so there is a possibility of computational gain. Therefore, it can be suitable for large mining. But nothing is free. When you make granulation, you lose information also. So depending on your demand and need, you go for coarser to finer granulation. For example, in granules, in age, not so young, very old, young lady, granule. When you drive a car, slightly left, slightly right, these are all granule. In a school, every section can be considered as a granule because this section is determined either by marks obtained in the previous class or by age group or by sex. Similarly, in image, as per similar color regions or similar intensity regions can be considered as granule. Similarly, as per Weber's law, 6 consecutive intensity, you cannot discriminate with your naked eye. So I can consider 1 to 6, 2 to 7 as my granule. So note that when I talk about granules, concept granule was embedded in fuzzy set theory because membership function granulates the feature space. And similarly, rough set, it is defined on granules. I will explain rough set in one slide. So fuzzy set and rough set become most powerful technology for granular computing. And rough set became more popular in data mining and knowledge discovery from heterogeneous data, where the statistical decision making does not work because data is heterogeneous. That means features are uncorrelated. When features are correlated, you have just several literature. But now the data you get, features are not correlated. So rough set. What is a rough set? Suppose this is an information system. X-axis, Y-axis. Within this X1, there is some called granule, because here you cannot discriminate given the relation between X and Y. Now, if I add one more dimension, then the granule size will be less. Now, within this, in an image, I can consider intensity of different regions. In a school, I can consider these are of different sections. Therefore, they have different sizes also. Now, over that, I defined a set, each set. And I ask you, what are the granules that will constitute this set? Now, you see that there is no unique answer. There is one granule, yellow mark, they definitely belong to this set. I call it lower approximation. And another set, orange, which includes this yellow set also. I call it upper approximation. These are the granules which definitely possible belonging to this set, and these are the granules which definitely as well as possibly belong. So if I subtract lower approximation set granules from upper approximation granule, I get the boundary granules. And these are the boundary granules, they create problem in decision making. And I can define the roughness of this granule as 1 minus cardinality of lower, upper. If lower equal to cardinal, roughness is 0. That means no granularity means no roughness. Roughness is coming because of the granularity. In an image, when you discretize in x-axis, y-axis, and z-axis, you introduce granularity. You lose information, you include granularity. And when you make a decision out of that, you incur uncertainty. Therefore, this rough set is a crisp set, but with rough description. Vague definition of this X in the universe in terms of lower approximation that signifies the incompleteness knowledge about you. Therefore, when you make a decision, we like to minimize this incompleteness. You can define entropy, very catchy term. You can just publish nice papers also. So we define entropy such a way that your incompleteness, you reduce entropy, minimize entropy, so the incompleteness, gain in incompleteness is minimal. Suppose in a school, some kind of contaminated disease has been spread. This is your set. Now the principal has to make a decision whether infected classes should be declared holiday or not. So how do you define infected classes? If all the students are infected, they have to be declared holiday. So this constitutes lower approximation. But there are some sections where not all the students, but one student was infected. So for them, the decision has to be taken by the principal whether they need to declare holiday. That creates uncertainty. I'm just trying to explain you very simple, because Professor Amit Ghosh told me, hey, don't talk other things. So simple. Professor Ghosh is okay? He's sleeping. Sleeping, okay. So this subject I picked up from NASA. When I was working at NASA, the East European scientists, they are very good in maths. They used to come for internship. I don't know how much many of you know, NASA not only does research in space, they funds to universities also for internship, PhD program, and also the small scale industries. So I used to listen their talks that time. I can see with my limited knowledge in pattern and image processing that time, back in 1988, you can use lower approximation for uncertainty because pattern and image processing we are handling, but use granular computing. Use granule and forget everything. So based on that, we have several applications, video tracking, microRNA selection bioinformatics, link prediction problem in social network analysis, air quality intervention. Recently, during pandemic, I hired a postdoc lady, chemistry. environmental data. Let us consider only video tracking as an example here. So if you consider these are all constituted called big data 2010. Big data means large volume, large velocity, large variety, veracity. That means your data size has gone to terabyte, and it's a velocity, tsunami, streaming data you are getting. And variety means heterogeneity, and veracity means conforming to facts. These 4 B's characterize what is called big data. Big data was a big buzzword around 2000, if you look at this one. Now, I'm giving one example of occluded objects. You are tracking an object, and it gets occluded. Still, you are able to predict with the help of rough set. What is a rough set? You remember? Lower approximation means definitely belonging. Upper approximation means definitely and as well as possibly belonging. So I take videos. Videos means sequence frames. At t, t-1, t-2, t-3. Let us take 3 previous frames. I compute neighborhood granules. That means you take a pixel, you color the color similarity with respect to threshold in RGB, red, green, blue. Let's consider one domain. So you compute the similarity and put a threshold. That's how you grow. It's called granule. Now within this granule, you take 3 frames, t, t-1, t-2, t-3. You take its union, so you get 1 frame. Now we take t to t-1, t-2 to t-2, t-2, t-3. You get 3 frames. So then you make 1 to p point convolution. That concept I borrowed from electrical engineering. We define this a neighborhood rough set filter. So I get input, 1-dimensional union, and 3 separate. And it's an unsupervised route. It outputs gives unsupervised, that without knowing the object, without knowing any prior information of these object models in 3 frames in terms of lower and upper. That means we are definitely belonging, and that could be possibly belonging. And based on this information, we model the nature of variation of the objects in direction, speed, and we approximate location in the Ft plus 1 frame. And there also we compute lower and upper approximation. I take the roughness measure. If it is minimum, you track. If it is not minimum, that means it is occluded. Then you use entropy, intrinsic entropy, and then I put so that the boundary upper minus lower, whether it would be put to lower or to be not lower. So this is a typical example. You have this 1 to p point convolution. Convolution layer operator is intersection and union. When you take intersection means that is the minimum amount which will be objecting belonging to the moving parts. You say you are taking many frames. Nah? So if you take the difference tau, so background gets subtracted. Only you are landed with the region which are moving parts. So if you use intersection and union, if you take intersection, you get the lower approximation. That means they will definitely belonging. And if you take the union, out of this union, you find those granules which have non-empty intersection with the lower approximation. That's how you get upper. So it is a lower approximation which definitely belong. This is upper. It's a lower possibly and upper belong. So you look at this London metro, it's a tracking. The frame per second 15 and p equal to 6. That means 1 minus 5 previous frames. See, a complete occlusion, we are prediction. Now, these are all machine learning. There is no other so far. But today, if you see that machine learning performance increases if your number of previous samples is more. And today, we have got abundant samples. So machine learning and deep learning, which is an advanced form of machine learning, has become a meaningful choice. Now, the problem is that when you have advantage, you have some overhead also. What are those overhead? Let's see deep learning. It learning in depth in different stages. This is just layman word. Learn in different stages. Now, what is the difference with the machine learning? So, machine learning algorithms, they are task specific, but here we get data representation specific. And deep learning process is very time consuming because you are using several layers. So, it's time consuming and difficult to engineer. So, therefore, our solution is, why don't you make it granulated deep learning? That means you reduce the computation time and improve the performance. Example. Now, convolutional neural network is a deep architecture suitable for image and vision videos. There are many architectures for time scale, time series data, LSTM model. For video temperature data, it's a CNN model. Now, CNN model provides the backbone for any video processing framework depending on the task. And what is CNN? It's an input layer, it's a convolution layer, max pool, rectified linear unit, then you can fully connect a neural network and output. This is a block diagram. Now, if you look at this, what you do in CNN, you slide a 3x3 mask and you make the convolution. Now, what we say, it is time consuming. So, it is an image, I can make it granulation. And if I granulate it, if I have 32 pixels and I reduce it to n, say 5 or 6, then the same granulated, same the convolution value I can put, I do not need to do for all the points, only I do once and then repeat. Therefore, I will drastically reduce the computation time, but with some accuracy. This was the concept we published in 20. Now, let's come for a multi-object detection with granulation. This is called AlexNet architecture, which uses 5 CNN models. What is called a region proposal network. That you first propose the region, two-stage detector, then based on the approximate regions, you extract the features and pies. This is a very highly speed, this is very widely used. Now, what we said, no, you take the videos, since you are given videos, you extract the temporal domain, you make the granulation in temporal domain, you make the granulation in spatio-color domain, and you take further intersection, so you develop spatio-temporal. That's how you are reducing the background, because I'm not interested in the background. I'm only interested in the object, foreground object. So then I get this ROI map, and out of those I go back to original pattern domain, image domain, and I take those. So as a result, what we are gaining, where videos are directly taken as input rather than static images. Only granules formed over this pool map are used for training and also defining the class for the recognizing the objects. Then only positive regions of interest are taken into account, and only FT regions corresponding to FT regions are taken. So improves real-time detection speed. I have 10 minutes. So let me consider a steel plant. In one of the steel plants, I am giving the data. So all a steel plant is a small, all kinds of cars, human being, they are tracking. So there you cannot use machine learning because it is a noisy, small objects, and also you cannot do feature extraction, then you followed by the classification, just like we do the face recognition problem. So here see the beautiful, it's a faster RCN which are available. Is originally is 29 frames per second, but I have reduced it to 10 frames just for your visualization. You can see that some of the bikes and are not being tracked. Now, if you go by the spatial color granulation, see that some of these RPN. See, some of the objects which you could not detect there, they are getting detected as marked by the yellow or red circle. See, red circle. Those objects which you could not be done there. Now, if you use the spatio-temporal domain, even it is the best one, even those which cannot be done by the spatio-color feature, still you are able to get one. You see, all these red circle indicates the objects which you could not, occluded objects which you could not detect there. So you see, one of in our steel plant in India. So this one is the last slide, my evolution of the discipline. Look at this. Pattern recognition, if you go to Google search 60s, in India it started in 70s, in Science, TIFR and ISI. Then image processing we started in 1970s when I went to Imperial College in here also, because image processing is more expensive. The AI machine learning expert system came in 80s, if you look at this, and knowledge-based system 1990s, data mining 2000s, big data 2010, today data-driven science. Now, every time when you have evolution, new approaches are defined for that handling the kind of data you are, kind of problems you have to handle. For example, when we started pattern recognition in 70s, we had large number of samples, small feature. So in order to find the best feature, we had to cluster in the sample space. But today, genes have few thousand, samples more, and those are uncorrelated. Therefore, you cluster in the featured domain in order to guess those segregate. And if you have reduced from few thousands to few hundreds, then take the centroids, you reduce the feature dimension. That is a highly cited paper in IEEE PAMI. New terminal, now it's a big hope, but certain concern. What is the caution about to them? Because if you want to know deep learning, you have to know shallow learning. If you want to know shallow learning, you have to know neural networks. If you want to know neural networks, you have to know pattern recognition. Without knowing pattern recognition, mother subject, if you want to jump from here, oh, you say AlexNet, you train, you result. Then after again 7 to 8 years, subject will die. Just like what will happen in 80s. So my request to beginner, if you want to research, because now money is with deep learning. Money comes with with data science. So if you want to do research, you find new architecture, you develop the mathematical framework. Don't rely on this. And you learn from examples. Machine learning means learning from previous examples. So in 80s, we have learned examples. I hope this will not recur. With this one, I conclude. I acknowledge my students and younger colleagues. I have worked 90% with my students and younger colleagues in India and abroad. And now National Science Chair that supports me 3 postdoctoral fellowship for the last 1 year, because before 2 years, we could not hire any because of the pandemic. Thank you. Wish you a happy New Year. Thank you very much.
Thank you. Many thanks, Professor Paul, for really wonderful talk and, opening up the bigger horizon of data science. Because of paucity of time, we won't be able to have the interactive session with Professor Paul. All the, interested scientists and students are suggested to interact with him during the tea session. So let us again join big hands for this wonderful talk.
Thank you very much. Thank you. Thank you.
So with this, we come to the end of the morning session. And there will be some announcement for the, subsequent sessions of today. And
Okay.
accordingly, we will reschedule our program.
Thank you, Professor Biswas, for the session. And as you know, the Professor Gautam Biswas, a very distinguished chairperson we had here, a product of IIT Kharagpur, director formerly of IIT Guwahati, and also CSIR, Central Mechanical Engineering Research Institute. So with this session ends, and we will be breaking for tea, but please try to be back here before 11:30 for the AGM, and the discussion can be had during the tea itself. Thank you so much. We'll meet here at 11:30.